So now we want to take a look at B, where we assume that the insurance company pays as long as just one is alive. So the interval of time in which there are benefit payments is as long as the remaining lifetime of the person who lives the longest. So as we drew up down here earlier, in case 2, we want to find the density of y, which is the maximum of the 2 lifetimes, since the amount of time that we pay in, it ranges all the way up to the time of death of the last person dying. So, what am I trying to say here? I'm trying to say that we want to find the density of y given as the maximum of the 2 remaining lifetimes. So let me just write that up. Goal, find the density Fy for y equal to the maximum of T1 and T2. So let's just consider one T1 and T2. Let's consider what values of y result from which values of T1 and T2. So what we can think about is, if both T1 and T2 are smaller than some value, then that must mean that y is also smaller than that value. If y is smaller than some value, it means T1 and T2 are also smaller than that value. We can't really use the same hint as we did earlier, because even if y is greater than some t, well, then it just means that either T1 is greater than that t, or T2 is greater than that t, and then we have a union. And it's not that fun to work with unions. It's more fun to work with intersections. So the thing that we're going to do here, instead of considering the probability that y is greater than something, is to first consider for t greater than 0, the probability that y is greater than, smaller than t. So the probability that y is smaller than equal to t. Now this probability is equal to the probability that the maximum of T1 and T2 is smaller than t, just by definition, right? Okay, so when is the maximum of T1 and T2 smaller than some value t? So what we can see is, if the maximum of T1 and T2 is smaller than a value, then that must mean that T1 is smaller than that value and T2 is smaller than that value. However, if both T1 and T2 are smaller than some value, that must mean that the biggest of them is also smaller than that value. So the implication goes both ways, which means that this event here is exactly equivalent to this event over here, which means that they have the same probability. So this above is equal to the probability that T1 is smaller than equal to t and T2 is smaller than equal to t. And again, by using independence of T1 and T2, this is equal to the probability that T1 is smaller than equal to t, multiplied by the probability that T2 is smaller than or equal to t. Now, this is given by the distribution function of an exponential distribution with parameter lambda 1. So I will just remind you guys that for an exponential distribution, let's just say, so for an exponential distribution with parameter lambda, the distribution function is given as 1 minus e to the minus lambda t. So the distribution function here is given as 1 minus e to the minus lambda 1t multiplied by 1 minus e to the minus lambda 2t. And when we multiply all of that together, what we get is 1 minus e to the minus lambda 1t minus e to the minus lambda 2t plus e to the minus lambda 1 plus lambda 2t. So when we want to find the density, what we do is we differentiate the distribution function, right? So hence, the density Fy of t is, so Fy of t is equal to d to t of the probability that y is smaller than or equal to t, so the derivative of the distribution function. This is also what we otherwise denote as f of t. And this is equal to, well, the 1 just disappears, right? And then I differentiate, so I get lambda 1 e to the minus lambda 1t. The next term gives me plus lambda 2 e to the minus lambda 2t. And then the last term gives me minus lambda 1 plus lambda 2 e to the minus lambda 1 plus lambda 2t. And this is the density of y, and there's no name for the distribution with this density, so we will just call it the distribution of the maximum of T1, the density of the distribution of the maximum of T1 and T2.